In this lesson, I just want to walk through the full steps for graphing a rational function as shown in your textbook. It is important that you understand how to graph using each of these steps and how they develop into the final graph of our function. So here we have f of x equals 3x minus 3 over x plus 2. So first we want to figure out the symmetry of the function. So whether the function is symmetric about the y-axis, the origin, or if it has no symmetry. So this goes back to finding our whether our function is odd or even. We can't use the shorthand that we had before by just looking at the exponents. That won't work here. That only worked for our polynomials. So don't assume that if our exponents are all even and the function's even, or if our exponents are all odd, the function is odd. We do need to go back to using that f of negative x. So first we'll try to figure out if the function is even, which would mean that it's symmetric about the y-axis. And in order to do that, we would need to show that f of negative x is equal to the original function f of x, which means we need to find f of negative x. So when we substitute that in, we're going to have 3 times negative x minus 3 over negative x plus 2, which gives us negative 3x minus 3 over negative x plus 2. So first we would say, okay, is this f of negative x that we have right now equal to the original function? We can see that it's not. The first term in the numerator, first term in the denominator have different signs. So that means as it stands right now, the function would not be even. But I can simplify this a bit. I can factor out a negative 1 in the numerator, and we would be left with 3x plus 3. I can also factor out a negative 1 in the denominator, so that way we're left with x minus 2. Then our negative 1s would cancel out, which means we're left with 3x plus 3 over x minus 2. So this is an equivalent form of f of negative x. So looking at this answer, we could say, okay, well, I have 3x plus 3 over x minus 2. Is that equal to the original 3x minus 3 over x plus 2? It is not. We can see that the sign between the terms, the numerator and denominator, are different, which means that f of negative x does not equal f of x, so the function is not even, which means that it is not symmetric about the y-axis. Next, we determine if the function is odd, which means that it would be symmetric about the origin. The function is odd if f of negative x is equal to negative f of x. So we're going to keep what we have with that 3x plus 3 over x minus 2. We're going to look at that a little bit later. But what I do need to figure out is what negative f of x equals. With a rational function, that negative stays in front, at least in terms of the notation. And then we have two options in terms of distributing the negative. We can either distribute it to the numerator or to the denominator. So first I'll distribute it to the numerator, so that way it becomes negative 3x plus 3 over x plus 2. And we'd say, okay, well, this is my first answer, so I have negative 3x plus 3 over x plus 2. Is that equivalent to what we had for f of negative x? If it is, then the function is odd. Well, if I look at f of negative x, we had 3x plus 3 over x minus 2. These are not equivalent to each other, so as it stands right now, the function is not odd. The other option would have been if I distributed the negative to the denominator. So the numerator would stay 3x minus 3, but the denominator would become negative x minus 2. So comparing this form, I would again see as negative f of x, so 3x minus 3 over negative x minus 2 equal to f of negative x, 3x plus 3 over x minus 2. Again, they are not equivalent to each other, so the function is not odd, so it has no symmetry around the origin. Since the function is not odd, it's not even, that really means that our function has no symmetry. Next, we want to look at our vertical asymptotes. So remember, for our vertical asymptotes, we do need to try to simplify the original f of x function. So I can factor out a 3 in the numerator. So that way we're left with x minus 1 over x plus 2. We want to do that to see if we can cancel out any factors, because when a factor cancels, that means that there's actually a hole at that value for x, not an asymptote. In this case, even though I could factor the numerator, I'm not able to cancel any factors, which means that I can just set my denominator equal to 0 to find my vertical asymptote. So we would have x plus 2 equals 0, which gives us a vertical asymptote of x equals negative 2. We do need to keep it as x equals the number in order to show that it's a line. So make sure it's x equals negative 2. Next, we want to find our horizontal asymptotes. When finding our horizontal asymptotes, we want to compare the degree of the numerator with the degree of the denominator. The degree of our numerator, 3x minus 3, would just be 1 because that is the exponent of our only variable x. It's going to be the same in the denominator because we have x plus 2. Our only variable x, again, has a power of 1. So the degree of the denominator is also 1. When the degree of the numerator is equal to the degree of the denominator, the way that we find the horizontal asymptote is by taking the coefficients of those terms. So that means we have y equals, the leading coefficient of our x in the numerator is 3. The leading coefficient of the x in the denominator is 1, so that gives us that our horizontal asymptote is y equals 3. Just like with our vertical asymptote, we need to make sure that we express it as a line, so we need to have that y equals in there. Next, we want to find our x-intercepts. So remember, to find our x-intercepts of the function, we would set the function equal to 0. Well, for our rational function, we would have 0 equals 3x minus 3 over x plus 2. When dealing with a fraction, the only way that we can get it equal to 0 would be if our numerator is equal to 0. So the shorthand to find our x-intercepts would be to just set your numerator equal to 0. So we would have 3x minus 3 equals 0. Solving for x, we have 3x equals 3. So then x equals 1. Now I suggest writing this as an actual order pair so you can distinguish between what was your vertical asymptote and what is your x-intercept. So that way this is the point 1, 0. Next we want to find our y-intercepts. Remember, when dealing with a function, in order to find our y-intercepts, we simply find f of 0. So we substitute 0 in for x. We have 3 times 0 minus 3 over 0 plus 2. So that means we're going to be left with negative 3 over 2. So again, since it is a point, I would express your y-intercept as the order pair 0, negative 3 halves. So up to this point, we did a lot of work. We found our asymptotes, we found our intercepts, we determined if there was some sort of symmetry. But it is important, in order to get the full graph, to find more points. And it is also important to understand what kind of points we need to find. So we can't just assume that we're going from -2 to 2. We can't really just pick any random points. There has to be some method. What we need to do is we need to find values that are between our asymptotes and between our intercepts, and really on either side of them. So if we look at, I'm just going to draw a quick number line, the values that we've found so far in terms of our intercepts and our vertical asymptote, is that we had our vertical asymptote at x equals -2. We had our x-intercept at 1, 0. And then we did also find our y-intercept with 0, negative 3 halves. So these x's, which is really what we care about to help make our table, I'll put that 0 in there because 0 is important. We want to try to find values that fall really to the left of -2, between -2 and 0, between 0 and 1, and then to the right of 1. Your vertical asymptote always separates the graph. Remember, with your vertical asymptotes, a graph can never cross a vertical asymptote. So if you have one vertical asymptote that we have here, we're going to have at least 2 pieces to our graph. If you had 2 vertical asymptotes, you would have 3 pieces. So we need to make sure to find enough points that we get a comprehensive graph. So first, we're going to start off with at least one number to the left of -2. I'm going to pick a few. I'll pick -4 and -3. Because those values are, again, to the left of -2. Then, between -2 and 0, I'm going to pick -1, and I'm actually going to leave a few open spaces here, and I'll talk about why in a minute. And then I need some value between 0 and 1, so maybe 1/2 or 0.5. And then I need at least one value to the right of 1, but again, I'll pick 2 and also 3 to make sure that I get a comprehensive graph. Again, you can actually pick different numbers than what I chose here, as long as you're meeting the requirements of finding some numbers to the left of -2, between -2 and 0, between 0 and 1, and then to the right of 1. So x equals -2 is your vertical asymptotes, that's separating the graph. X equals 0 is actually your y-intercept. And then x equals 1 was our x-intercept. So those are our key points on our graph that we found so far, except for our horizontal asymptote. We don't really need to use that here. In order to help us to make a table of values to find additional points. So I did leave 2 spots open, and I left them open where that -2 would have been. It's important to understand what's happening with the end behavior of an asymptote. So what I like to do, although this is not required, but what I like to do is to pick some values that are pretty close to -2 and on either side so we can see what's happening. Because just because the graph is going up on one side of the asymptote doesn't mean that's going to be going up on the other. So usually I try to go either a 10th or 100th in either direction. So for example, if I take -2.01 and then on the other side -1.99. So that way you can see what's actually happening with the graph to the left and to the right of -2 with that asymptote. So, at this point, you want to use your calculator. Okay, we have our calculator. Definitely we're going to be checking our answer on our calculator, but you want to use your calculator to get these f of x values. You want to use the table feature. Make sure that when you're typing into y equals, you're typing the function as with parentheses, 3x minus 3, close the parentheses, divided by parentheses, x plus 2, close the parentheses. It's definitely if you're using a TI-83 or an older TI-84. Some of you, when you hit the divided by, it might turn it into a fraction automatically, which is great, but you want it to just make sure that it looks like 3x minus 3 over x plus 2. Then, when you're using your calculator, you would hit second graph, and that will give you a table of values, and you can scroll up or down. That would be the fast way to try to get your whole number values. So for your whole number values, then we should have our -4 was about 7.5, -3 was 12, -1 is -6, 2 is 0.75, and then 3 is 1.2. Now your other values at -2.01, -1.99, and 0.5, you won't be able to see it in your table. There is a method to use your table in order to evaluate these if you wish to do it that way, and you know how. My suggestion is to actually use the y-vars feature, and I've linked a video in the course in order for you to see how that works. But what you can do is on your home screen, you hit the vars button, you go over to y-vars, you're going to hit enter for function, hit enter again for y1, and then you would have y1 in parentheses. You would put, for example, -2.01, close the parentheses and hit enter, and what it does is that it evaluates -2.01 in what you put into y1 in your equation before. You can do that again for -1.99, you can do it again for 0.5, and then that way you're not trying to sit there and do too much work with your calculator. I mean, it gets, a little tedious if you're trying to type in using the correct parentheses with the original f of x equals 3x minus 3 over x plus 2. Either way, -2.01 is about 903, so a very large number, and -1.99 is -897, so a very small number, and then 0.5 is going to be -0.6. So this gives us a comprehensive table of values, which is going to help us to graph our overall function. Finally, now we're up to using the information that we obtained to graph the function. So first, remember we said that there was no symmetry, so we can't really do too much with that information. Next, we found there was a vertical asymptote at x equals -2. So we want to put that in as a dashed line, and we can even note it up here as x equals -2. Next, we found there was a horizontal asymptote at y equals 3. So y equals 3 would be a horizontal line. Again, writing that as dashed. So we have y equals 3. Next, we found that there was an x-intercept at 1, 0. So we want to plot that. Then we found that there was a y-intercept at 0, -3/2, so -1.5. And then last was our table of values. So as we can see so far, just from the information that we have, is that our vertical asymptote separated our graph into two halves, right, to the left of it and to the right. Using just the information that I obtained from parts A through E, we only really have what's happening with the graph to the right of the vertical asymptote. If I didn't make that additional table of values, I wouldn't have these other points, anything really to the left of x equals -2. So I'm going to do my best to graph most of the points that we have. So -4 would go to 7.5. Then -3 would go to 12, so it's a little bit off the graph. So, you know, we can approximate or at least understand that it's going to be going up here somewhere. And with these large numbers, you really don't have to graph them, as long as you just understand that that's what's happening with this function, is that the end behavior is that it's drawing it up to positive infinity. So if you wanted to put it up there, you can, but it's just important to understand that the graph's going to be riding along, going up to positive infinity. Same idea with the -1.99, that's a really small number, so you're going to be way down at the bottom of your graph somewhere. Then for -1, you're going to be at -6. At 0.5, you're going to be at -0.6. And then at 2, you're going to be at 0.75. And then at 3, you're going to be at about 1.2. And then from here, we can see that we have our two parts of the graph. So we're going to end up with, to the left of our vertical asymptote, it goes up to positive infinity. But then eventually it's going to end up coming down and riding along our horizontal asymptote. For our right side of our vertical asymptote, we know that we're going down to negative infinity as we get close to the asymptote, and then we're going to be riding along our horizontal asymptote. And again, definitely you can use your calculator to check your answer to see if we get the same picture, and hopefully we should.